Hello class. In this lecture, we will learn resistance and resistance capacitance firing circuits.
A unijunction transistor consists of an N-type base to which a P-type emitter is embedded. The N-type base is lightly doped. The P-type base is highly doped. Two ohmic contacts B1 and B2 are provided at each end. The UJT has three terminals: emitter, base 1 and base 2. Between base 1 and base 2, unijunction transistor behaves like an ordinary resistance. RB1 is the internal resistance from base 1 to eta point A. RB2 is the internal resistance from base 2 to eta point A. With a voltage VBB applied between the terminals B2 and B1, the voltage at point A, that is eta point, with respect to B1 is given by voltage divider rule. Therefore, VAB1 is equal to VA, that is equal to VBB into RB1 divided by the total, that is RB1 plus RB2. The same is written over here, VBB into RB1 divided by RB1 plus RB2. Replacing RB1 divided by RB1 plus RB2 by eta, we have VAB1 is equal to eta VBB, where eta is the ratio of RB1 to RB1 plus RB2 is the intrinsic standoff ratio. Typical values of eta are 0.51 to 0.82. Interbase resistance RB1 plus RB2 is of the order of 5 to 10 kilo ohm. The emitter is nearer to base 2. Therefore, resistance RB2 is less than resistance RB1. The DC voltage source VBB between base 2 and base 1 is constant. DC voltage source VEE between emitter and base 1 is considered as the input. The Ujt equivalent circuit is shown in the dotted rectangle. The magnitude of voltage VE can be controlled by varying the resistance RE. The voltage at point A is eta VBB. As long as emitter voltage VE is less than the eta VBB, emitter base 1 junction will be reverse biased. Hence, emitter current IE is negative as shown by the PS region. The region PS has very small current and hence it is treated as off region of the UJT. The resistance between emitter and base 1 junction is therefore very high. At point S, IE is 0. Since IE is 0, drop across RE is 0. Therefore, potential at point E is VEE. That is, OS will be equal to VEE. The UJT is in off state as long as the emitter voltage VE is less than eta VBB plus the diode voltage drop. When VE equal to eta VBB plus VD, diode voltage. When VE is equal to eta VBB plus VD, point B is reached and emitter base 1 junction is forward biased to allow diode current. Point B is called the peak point voltage. Vp is the peak point voltage. Ip is the peak point current. When the emitter voltage reaches Vd plus eta VBB, the highly doped emitter injects holes into the lightly doped base region. Since the base region is lightly doped, the holes rarely get a chance to recombine. The lower base region is filled up with additional current carriers, that is, holes. As a result, resistance of emitter base 1 junction reduces. As RB1 reduces, the potential VAB1 reduces. This drop in VA in turn causes VE equal to VD plus VA to fall. As VEE is constant, fall in VE results in more emitter current, IE. As IE increases, more holes are injected into the base region, thereby reducing the resistance of RB1. As IE increases, the value of RB1 decreases and more holes are injected into the base region, thereby further reducing RB1 and so on. This regenerative or snowballing action continues up to a point when RB1 reaches a small value. The emitter current IE is given by VEE minus VD divided by RB1 plus RE. When RB1 has dropped to a very small value, as indicated by point C, the UJT has reached the on state. At point C, base region has completely saturated and RB1 cannot decrease any further. Point C is called as valley point. VV is the corresponding emitter potential, IV is the corresponding emitter current. At point C, UJT is on. After UJT is on, an increase in VE has an increase in IE too. This is indicated by CQ. At point Q, VE is a little more than the valley point voltage VV. Between points B and C, as the emitter voltage falls, the current increases. Therefore, UJT exhibits negative resistance between these 2 points. The negative resistance region BC between the peak and valley points gives UJT the switching characteristics for use in SCR triggering circuits. At valley point, the current is given by IE equal to VV upon RB1. Valley point current is also called as holding current, which keeps the UJT on. When emitter current falls below valley point current, UJT turns off. Figure shows a Ujt relaxation oscillator. The emitter of the UJT is fed from an RC circuit. The potential at the capacitor decides whether the UJT is on or off. The resistance will decide the rate at which the capacitor charges. The UJT is in off state as long as emitter voltage is less than eta VBB plus VD, that is peak point voltage. Suppose the capacitor has a charge of valley point voltage. Since the voltage of the capacitor is below the peak point voltage, the UJT is in off condition. Since UJT is in off condition, the capacitor will charge from the source through the resistance R. This capacitor will charge up to peak point voltage and the UJT is off. As soon as the capacitor voltage tries to exceed beyond peak point voltage, the emitter potential will rise beyond peak point voltage and the UJT will turn on. Since the UJT turns on, the capacitor discharges through the emitter base 1 junction. The discharge action of the capacitor is shown over here. Since the capacitor is discharging in this region, the voltage across R1 is the discharge part of the capacitor. Therefore, the output voltage is the discharge part of the capacitor. When the capacitor voltage reaches valley point voltage, the UJT turns off. As soon as the UJT turns off, the capacitor starts charging towards Vp again through the resistance R. The cycle continues and we will get a train of pulses across resistance R1. This train of pulses can be used to turn on an SCR.